Discrete Map has three sections: a clock section, an event section, and a map section. The clock section creates a ramp wave, which you can see as the blue line here. Each cycle of the ramp represents one musical cycle, whether that is a measure, a phrase, or whatever else. The ramp has a rate control with an audio and sub-audio range, a linear modulation input, as well as a volt per octave input. It goes from 4 minutes per cycle to 12 kilohertz. The clock is specifically built to interact with other modules, with a sync input, a sync every nth pulse input, an end of cycle output, and a one-shot mode. The ramp can be obtained directly from the ramp output, which is normal to the X input of the event section. The event section activates one of the 8 stages when the X input moves past a threshold set by the bottom sliders and the direction switches. There are 2 modes for setting these thresholds: by absolute position or relative duration. Additionally, these thresholds can be modified by above and below, as well as directly with CV from the expander. The map section maps the currently activated stage to the f of x output according to the top sliders and the plus y or transpose input. The sliders can be switched between a 10, 5, and 2.5 octave range. Additionally, when each stage is activated, a gate will be produced ranging from 5 microseconds to 3 seconds long. A gate to the external input will cancel the active stage. We'll begin by explaining this with an external input. So into the X input here, we have a sine wave, which is the blue line on the screen, and we're not using the clock section at all. As the sine wave rises past each of these thresholds, that stage is activated, and the other stages are deactivated. If instead we have these set to fall, when it will fall past those thresholds, then that stage will be activated. And of course, the useful part of this is not just that we can have an interestingly timed sequence, but also that we can time that sequence along with a smooth contour in some other way. So here I have this going into the stride input of the harmonic shift oscillator. And we have a different tuning for each of these as the stride's being adjusted with the same sine wave that's driving the clock. The position of each of these is in order right now because that's the easiest way to think of it, but they don't have to be in any kind of order. So we can easily move a stage forward and backward past other stages and change the order. Using the internal clock, it's often helpful to have length mode engaged. In length mode, you can set the relative length of each stage based on the relative position of each of these sliders. So for example, if I push X2 all the way to the top, X2 now takes twice as long as all the rest. Let's adjust some of the others. Because nothing's happening with the clock, the measure always takes the same amount of time. So causing one stage to take more time will steal a little bit of time from the rest, and causing one stage to take less time will give a little time to the rest. That sounds complicated, but generally it's pretty intuitive. You just sort of decide what your baseline is, and then put everything at the divisions or multiples of that baseline. Because they're all relative, where that baseline is doesn't really matter. So for example, all of the stages are the same time in this setup. All of the stages are the same time down there. And all the stages are the same time here. It doesn't really matter. When using external CV with the expander, no matter what mode you're in, the CV will always add to that stage. So for now, X4 is being pushed back and forth. You can see sometimes it will overtake or go behind the stages before and after it. Of course, this really starts to shine when it syncs to something other than a traditional clock or a traditional, just simple LFO. Often in modular, you have this phenomenon that I would call modular time, where rather than having some simple oscillator or clock drive everything, you have some interaction of several different parts. And these parts together make the rhythm. So here, what we have happening is several LFOs are going into Babel to create a complex LFO, which is this blue line on the screen here. That then is being fed to the level control of the harmonic shift oscillator. So we're getting this drone, but a rhythmic drone that's controlled with LFOs. Now, what if we want to make a sequence based on that? So I'm going to take that and put it into the X input here. And I already have the sequence set up, so we just need to take the gate out. See here, the meter is tracking this X input, which is this complex LFO. We have some of these set to rise and fall. A couple of them are just off. Thing that's often helpful when doing a patch like this is to have two sliders at the same or nearly the same position but opposite polarities. much more complicated stuff is possible, of course, but we'll leave it at that for now. One of the interesting sources of rhythm for the discrete map is beat frequencies. When two sound waves sound at the same time, they create a shifting pattern of constructive and destructive interference, which we hear as a kind of pulse in the harmonics. To extract this, we can use a resonant filter to grab a particular harmonic, and an envelope follower to get the contour of that harmonic as it changes over time. In this patch we have two sawtooth waves, one produced by the triphase oscillator and the other produced by the discrete map clock section. We can use one inertia as a resonant filter, and a second inertia as an envelope follower. We'll take that extracted envelope and plug it into the X input of discrete map. As we play different notes, the way this beat frequency works will change, and we'll get different sequences. This patch is illustrating several things. Let's start with clock sync. On the discrete map, there are two sync inputs, sync and sync over n. Sync immediately syncs the ramp to the bottom on every pulse it receives. It's usually useful for synchronizing with some pulse that tells us where the start of a measure or phrase is. The sync over n input will count the pulses it receives, and only sync after it receives n pulses, set with the knob here between 1 and 16. In this patch, we're using this in one of the simplest ways possible. We're just syncing to every 4 cycles of a square wave LFO. The LFO is also triggering an inertia, set up as a kick drum, giving us a 4-to-the-floor kick under our sequence. To get this set up, we've set the clock to once mode, so we ignore the internal reset, and then just some patient tweaking of the rate knob will do it. It doesn't have to be perfect, since you're going to be adjusting the positions on each stage anyway, but it helps to be as close as possible, especially in length mode. The other thing this patch is doing is making use of the ABC expander to sequence changes in the timbre of the sound. The ABC expander groups the stages into 3 groups, A, B, and C, produces a per group gate, and connects a sequential switch according to the group setting. It also groups threshold CV, but we aren't using that in this patch. Most of the stages are set to A, which isn't doing anything. Stage 3 and 4 are set to B, and the B gate is adding additional rise time to the envelope. Only one stage, 7, is in group C. The C gate is used to increase the fall time of the envelope. But also, when group C is activated, the common jack is connected to the C jack, and we get a sequenced connection between a quick LFO and the FM input of the triphase, giving some vibrato on step 7. While of course the discrete map is designed to do unconventional sequencing, that doesn't mean that it can't work alongside a conventional sequencer. So here I have the SQ1 hooked up to this, and I have 2 sync inputs. One is going to the sync always input, and the other one is going to sync over N with it set to 16 cycles. I'm only going to use 8 steps in this, but we'll have a sequence here that repeats for every 2 sequences of this. We're using the hard sync input because we want to be able to line it up with 1 really easily. So you'll see. It's pretty simple and straightforward. While I have this patch on, I'm going to demonstrate something else. With the above and below controls here, control where the top and bottom of these sliders are. So they don't actually affect the CV directly, but more indirectly by changing all of them, all the sliders at once. So I'm going to plug 2 LFOs that are 180 degrees out of phase. What we'll see is that the range in which the sliders respond will contract to 0 and then reverse. But at the same time, we'll still kind of get the same sort of rhythms because we're still syncing to this clock and the clock itself is not being affected. One other thing to note, as you can see, the ramp is going up at the same rate, but the display here is actually relative to whatever the top and bottom of the sliders are. So when you change it with above and below, this will change. Of course, that's not the only way that you can hook up the discrete map in an external sequencer. Here we're actually driving the clock of the external sequencer with the end of cycle output. So basically, every time the saw wave resets inside of the discrete map, this will advance 1 pace. Then we're taking the output of this to the plus Y input of the discrete map in order to get a changing sequence with each step. So let's hear it. In a sense, every sequencer is digital. That's what discrete means in discrete map. But discrete map is built with individual logic chips, analog oscillators, and analog comparators, so it lacks a lot of the problems of conventional microprocessor-based audio. It doesn't have a sample rate or a Nyquist frequency, and it doesn't alias the way most digital audio does, which is all to say that it sounds awesome. At audio rate, discrete map can function as a graphic VCO. Just use the upper sliders to draw the waveform that you want, and that's what you'll get on the f of x output. can use the bottom sliders to change the width of each part of the wave, as well as its position. The rate control lets you do linear FM. The sync control is just like hard sync on an oscillator. And the sync over N control lets you do frequency division. Using the above or below jacks, you can get a sort of pulse width modulation for the entire wave. With the expander, you can do some interesting kinds of phase modulation. You can break the wave up into sections and modulate them each individually. Tracks volt per octave too, if you're into that sort of thing. In this patch, Discrete Map functions as, well, a map. Here we're running Discrete Map with an audio rate input. Half the sliders on rise, the other half fall. Right now, the top sliders mirror the bottom sliders, which gives a sort of bit crushing effect. More precisely, the continuous values of the sine wave input are mapped to discrete values in the output. But unlike a traditional bit crusher, we have full control over how that mapping occurs. Let's hear what happens as we change it. Here it is with a familiar pattern. think that there's many species of mixing, and Discrete Map introduces a new species, temporal mixing. While conventional mixing controls how much volume each wave gets, temporal mixing controls how much time each wave gets. In this patch, we have 3 different sine waves into the A, B, and C input to the switch. As we raise or lower the length of each active stage, the amount of time each wave gets will be increased or decreased. Switch only has 3 inputs, you can use additional stages to create more complex temporal patterns. Technically, temporal mixing is a kind of amplitude modulation. It feels very different. It's very much its own thing. Patch inspired by Suzanne Ciani's use of the Buchla Marf. We have Discrete Map sending a gate to an external sequencer to get 2 more melodic lines. All 3 lines go into the A, B, and C inputs of the expander, taking the output from the common jack. Using the ABC switches, you can switch whether a given step comes from the first, second, or third sequence, building complex, performatively changing sequences. this last patch is a probability sequencer. So what's going on here is Discrete Map is running at audio rate, and it's being slightly modulated by an LFO just to make it a little bit less predictable. It's in length mode, so the sliders control how long each of these will be present. But then we're taking the output, and rather than taking the audio rate output itself, we're taking it through a sample and hold. And so the sample and hold is grabbing one of these steps whenever it needs a note. So by adjusting the length of time that each step is active for, you adjust the probability that it'll be grabbed.